Section: Introduction. In this section, we delve into the comparison between Mamba-based and transformer-based large language models, LLMs, trained on extensive datasets. Our main aim is to conduct a thorough comparison between Mamba, Mamba-2, Mamba-2 hybrid, comprising Mamba-2, attention, and MLP layers, and transformers for 8 billion parameter models trained on up to 3.5 trillion tokens, using the same hyperparameters. We assess these models across 35 popular downstream language modeling tasks, ensuring a standardized evaluation setup for both Mamba-based and transformer models. Our experiments reveal that while Mamba and Mamba-2 models excel in language modeling tasks, they fall short compared to transformer models in terms of in-context learning and information recall from the context. This aligns with recent findings at smaller scales. Notably, pure structured state space models, SSMs, encounter challenges with tasks like the standard 5-shot MMLU and 2-shot phonebook tasks, where they exhibit lower accuracy compared to transformer models, even with increased training tokens. To address these challenges, we explore the potential of hybrid SSM transformer models, combining Mamba-2, self-attention, and MLP layers. Through ablation experiments, we optimize an 8 billion parameter Mamba-2 hybrid model with a specific layer distribution. Extensive evaluations demonstrate that this hybrid model matches or surpasses transformers on various natural language tasks, especially excelling in short context benchmarks and long context extensions. The hybrid models prove adept at handling information over long contexts, although they face difficulties in certain multi-document question-answering tasks. By leveraging global attention without explicit position encoding, the Mamba-2 hybrid models exhibit generalization beyond their trained sequence length, unlike models using windowed attention. Notably, a Mamba-2 hybrid extended to support 128K contexts performs exceptionally well on tasks like the phonebook lookup, showcasing the potential of SSM-based models for efficient language model inference without compromising accuracy or training efficiency compared to transformers. We share our findings to underscore the promise of larger-scale SSM-based models and aim to spark further interest in Mamba-based LLMs within the research community. Additionally, we make our code for training Mamba, Mamba-2, and Mamba-2 hybrid models available through NVIDIA's Megatron LM library and release model weights for Mamba-2 8B and Mamba-2 hybrid 8B on Hugging Face. Section Summary. In this section, we provide a comparison between Mamba-based and transformer-based large language models, LLMs, trained on extensive datasets. Our goal is to rigorously compare Mamba, Mamba-2, Mamba-2 hybrid, and transformers for 8B parameter models across various natural language tasks. While Mamba models excel in language modeling tasks, they fall short compared to transformers in in-context learning and information recall, leading us to explore hybrid SSM transformer models that show promise in overcoming these challenges while maintaining efficiency and accuracy. Section: Preliminaries. In this section, we will briefly discuss our implementation of SSM layers in Megatron LM and talk about the training data and evaluations used in our report. To support efficient large-scale training, we have implemented Mamba and Mamba-2 layers with support for tensor, sequence, and pipeline parallelism. The tensor parallel support for Mamba layers requires 2 all reduces per block, while Mamba-2 requires only 1 all reduce per layer but uses group norm instead of layer norm for internal block normalization. We have observed that using group norm does not affect validation loss as long as the group size is larger than 256. To create SSM transformer hybrid models, we combine Mamba or Mamba-2 layers with self-attention and MLP layers in Megatron LM. These layers support various parallelization strategies, allowing us to train hybrid models with tensor, sequence, and pipeline parallelism. For training data, we use 1.1T and 3.5T token datasets consisting of 70% English, 15% non-English, and 15% code. These datasets are predecessors of the NEMOTRON4 training dataset. We utilize a vocabulary of 256K tokens trained with sentence piece. In terms of evaluations, we use open-source LLM benchmark suites for standard and reproducible evaluations. We evaluate various tasks such as Wino Grande, PIQA, Hella Swag, Arc Easy, Arc Challenge, MMLU, OpenBook QA, Truthful QA, PubMed QA, Race, Natural Questions, NQ, and Squad V2, among others. These tasks involve measuring the model's performance in tasks like accuracy, normalized accuracy, and exact match. For long context models, we evaluate tasks like narrative QA, Casper, quality, multi-field QA English, Hotpot QA, 2Wiki MQA, Musique, TREC, and Trivia QA. These tasks require the model to answer questions based on long input documents. We also assess the model's performance on synthetic tasks like the phonebook task and tasks from the ruler benchmark, which test the model's ability to retrieve and aggregate information across long input texts. Section Summary. In this section, we implement SSM layers in Megatron LM, including Mamba and Mamba-2 layers supporting tensor, sequence, and pipeline parallelism. We found that Mamba-2 layers with group norm instead of layer norm showed no difference in validation loss when the group size was larger than 256. Additionally, we train our models on 1.1T and 3.5T token datasets, and evaluate them on various tasks using open-source LLM benchmark suites to ensure standard and reproducible results. Section: Mamba and Mamba-2 compared to transformers. In this section, we discuss our observations and experimental results from training 8 billion, 8B, parameter Mamba and Mamba-2 models and compare them with 8B parameter transformer models. We found that Mamba and Mamba-2 can perform as well as or even better than transformers on standard zero-shot tasks. However, they fall behind on MMLU and copying tasks, which we will explain further in the upcoming sections. When it comes to the model architectures, we trained Mamba, Mamba-2, and transformer models with specific designs outlined in a table. Our 8B transformer model is structured similarly to GPT-3, consisting of 32 layers with a hidden dimension of 4096. We use various components like attention heads, MLPs, activations, layer norm, and position embeddings to enhance the model's performance. Similarly, for Mamba and Mamba-2 models, we have specific configurations such as hidden dimensions, layers, state dimensions, activations, and normalization techniques. In terms of training hyperparameters, we used different settings for datasets of 1.1T and 3.5T tokens, adjusting batch sizes, learning rates, warm-up steps, learning rate schedules, weight decay, and optimization methods. We ensured that the hyperparameters for Mamba networks were aligned with those of transformers for a fair comparison. Our empirical evaluation of Mamba and Mamba-2 on downstream language modeling tasks revealed interesting findings. Both Mamba and Mamba-2 models showed comparable or better performance than transformer models on various tasks. Notably, pure Mamba-2 models outperformed Mamba models on average. However, we observed that MMLU accuracy was notably lower for pure SSM models compared to transformers when training on a shorter token horizon. Increasing the number of tokens improved Mamba-2's performance on MMLU, narrowing the accuracy gap with transformers. Further details on the MMLU results will be discussed in the following section. Section Summary. In this section, we compare the performance of our 8 billion parameter Mamba and Mamba-2 models with 8 billion parameter transformer models. We find that while Mamba and Mamba-2 can match or surpass transformers on standard zero-shot tasks, they fall behind on MMLU and copying tasks. Our experimental results show that Mamba and Mamba-2 models exhibit competitive performance compared to transformers on various natural language understanding tasks, with Mamba-2 models showing improvement in accuracy on MMLU tasks with increased training token horizon. Section: A closer look at MMLU. In this section, we explore the differences in accuracy of MMLU between pure SSM models and transformers. We tested our 1.1T Mamba, Mamba-2, and transformer models on various instances of this task to understand this accuracy gap. Typically, MMLU accuracy is determined by presenting the model with a question containing 4 answer choices, labeled A, B, C, and D. The model then predicts the most likely answer based on the probabilities it assigns to each choice. However, MMLU accuracy can also be assessed by calculating the probability of the entire answer choice following the question or using a close format where only the question is provided, and the model uses the answer texts to make predictions. We compared the performance of our 8B parameter pure SSM and transformer models trained on 1.1T tokens using these different MMLU evaluation methods. While the pure SSM models struggle with the standard and choice text in targets formats, they actually outperform the transformer in the close format. This suggests that pure SSM models possess similar knowledge to transformers but may require more training to excel in multiple choice question formats. The transformer's self-attention mechanism is adept at routing knowledge from various examples, which aids in answering questions effectively. Additionally, we examined the performance of the Mamba-2 hybrid model trained on 3.5T tokens and found that it narrows the accuracy gap with the transformer. However, the transformer still shows superior in-context learning capabilities, as evidenced by its significant accuracy improvement when transitioning from 0 to 5-shot scenarios compared to the Mamba-2 model. Moving beyond language modeling tasks, we also assessed pure SSM-based models against transformers on the synthetic phonebook task. This task evaluates a model's ability to learn in context and recall information. The transformer model demonstrates near-perfect accuracy for phonebook lengths up to its pre-training context length, while the Mamba and Mamba-2 models start to struggle with longer input sequences. Even with extensive training, the SSM models exhibit fuzzy memory, providing responses that are close but not exact matches to the correct answers. We also explored whether changing the phonebook prompt could enhance the SSM model's performance. By prompting the model with the name before presenting the phonebook, the reversed formulation, we observed improved accuracy for the SSM models, especially with longer phonebooks. However, challenges persist for the SSM models in determining what information to retain or discard for optimal performance on this task. Fine-tuning the Mamba and Mamba-2 models on the phonebook task could potentially lead to better accuracy. Section Summary. In this section, we explore the differences in MMLU accuracy between pure SSM models and transformers by testing our 1.1T Mamba, Mamba-2, and transformer models on various instances of the task. We find that while pure SSM models excel in the close setting, they struggle with standard and choice text in targets formulations, suggesting that transformers may have superior in-context learning capabilities. Additionally, when evaluating these models on the synthetic phonebook task, we observe that the transformer model outperforms Mamba and Mamba-2 in recalling phone numbers accurately, especially for longer input sequences, indicating that SSM models have challenges in deciding what information to retain or discard. Section Takeaway. In this section, we conducted experiments training 8B parameter Mamba and Mamba-2 models. Our findings revealed that these models perform similarly or better than transformers on many standard natural language tasks but struggle with certain tasks like MMLU and phonebook. We believe this difficulty arises because these tasks demand in-context learning, information sharing between tokens, and context copying. To address these challenges, we explored the idea of incorporating transformer layers, consisting of self-attention and MLP layers, into the architecture of our models. We created hybrid models combining Mamba, Mamba-2, self-attention, and MLP layers to enhance the model's ability to extract information from the context and facilitate in-context learning. Our journey to design the hybrid model architecture began with ablation studies. We ensured that all model variants had an equal number of parameters per layer to maintain consistency. By adjusting the number of attention heads and the MLP expansion factor, we balanced the parameters in self-attention and MLP layers with those in Mamba layers. We investigated how the ratio of self-attention and MLP layers in a hybrid model influences model performance. Our experiments with 130M parameter models revealed that having around 8% self-attention layers minimizes validation loss. We also found that allocating 30% to 50% of the layers to MLPs does not increase model loss and can even improve training efficiency. Next, we explored the impact of adding rotary position embeddings, ROP, to self-attention layers in hybrid models. Our experiments with an 840M parameter Mamba hybrid model showed that using ROP did not significantly affect accuracy. Therefore, we decided to exclude ROP position embeddings in larger-scale hybrid models. We further investigated the arrangement of Mamba, MAMBA2, self-attention, and MLP layers in the model architecture. Our experiments indicated that evenly distributing self-attention and MLP layers throughout the model yielded the best results. We also found that using group query attention, GQA, instead of multi-head attention, MHA, in self-attention layers had minimal impact on model quality but reduced computation and memory requirements during inference. Overall, our experiments and analyses guided us in designing effective hybrid SSM transformer models to enhance natural language processing capabilities. Section Summary. In this section, we experimented with training 8B parameter Mamba and Mamba-2 models, finding that they perform comparably or better than transformers on some natural language tasks but struggle with others like MMLU and phonebook due to the need for in-context learning and information routing. To address these challenges, we explored hybrid models combining Mamba, Mamba-2 with transformer layers, adjusting the ratio of self-attention and MLP layers to optimize model performance. Our findings suggest that incorporating a small percentage of self-attention layers, around 8%, and a higher ratio of MLP layers, between 30% to 50%, can enhance model efficiency without sacrificing accuracy. Additionally, we discovered that using group query attention, GQA, instead of multi-head attention, MHA, in self-attention layers can reduce computational and memory requirements for larger-scale hybrid models while maintaining model quality. Section: Mamba-2 Hybrid 8B. In this section, we trained an 8B parameter hybrid SSM transformer model with a specific architecture. Our model consists of 56 layers, with 4 self-attention layers, 24 Mamba-2 layers, and 28 MLP layers. Unlike using a repeated hybrid block structure, we arranged the layers so that a Mamba-2 layer comes first, and the attention and MLP layers are evenly spread throughout the model. We chose Mamba-2 for the SSM layers because it is faster than Mamba in processing SSM scans. Our experiments showed that 8B parameter Mamba-2 models perform as well as or better than 8B parameter Mamba models on various natural language tasks. For the Mamba-2 layers, we used specific parameters like an internal state dimension of 128, 8 groups, a head dimension of 64, and other settings. Throughout the model, we maintained a hidden dimension of 4096 and used JELU activation. We included skip connections and normalization before each Mamba-2, self-attention, or MLP block. We did not use dropout, biases for linear layers, and used separate parameters for model embeddings and output layer weights. Our Mamba-2 Hybrid 8B model was trained on large datasets using the same hyperparameters as transformer models. We were able to efficiently train our model on thousands of GPUs and compared its efficiency with transformers using model flop utilization, MFU. During inference, the hybrid model showed speed advantages over the transformer model, especially for long context lengths. The hybrid model also outperformed the transformer on various natural language tasks, showcasing its potential for faster inference and better model quality. Overall, our results suggest that a hybrid model combining Mamba-2, self-attention, and MLP layers can achieve higher accuracy and efficiency compared to pure Mamba-2 and transformer models across different natural language tasks. Section Summary. In this section, we describe the architecture and hyperparameters of our 8B parameter hybrid SSM transformer model, Mamba-2 Hybrid 8B. The model consists of 56 layers, with a mix of self-attention, Mamba-2, and MLP layers distributed strategically throughout. Our experiments demonstrate that the Mamba-2 hybrid model outperforms both pure Mamba-2 and transformer models on various natural language tasks, showcasing its efficiency and effectiveness in training and inference speed. Section: Long Context Evaluation. In this section, we assess the ability of hybrid SSM transformer models to handle long contexts. We trained two Mamba-2 hybrid 8B extensions, A16K and A32K variant, and compared them to the corresponding 8B transformer extensions. We extended the base models, which were pre-trained using sequence lengths of 4096, to 16K and 32K versions by further pre-training them on larger context lengths. We employed full global attention in the 4 self-attention layers. For this study, we utilized the same data as in our 3.5T dataset, without explicitly selecting long documents but instead using packed sequences to create 16K and 32K inputs for the model. All long context models underwent additional training with 50B tokens, with a learning rate that increased linearly over the first 1.7B tokens and then decayed according to cosine annealing. The maximum learning rate was set at 3E5 and the minimum at 3E6. To adapt the rope base frequency for the longer context lengths in the transformer extensions, we employed dynamic NTK scaling. We first evaluated the 16K and 32K Mamba-2 hybrid and transformer models on 12 standard natural language tasks. These tasks do not specifically require long context abilities, but we wanted to check if extending our models to long context variants affected their accuracy on common tasks. On average, we found no decrease in accuracy for the long context variants on these tasks. In fact, the 16K and 32K models showed slight improvements compared to the base models due to encountering 1.4% more data. Additionally, the 16K and 32K Mamba-2 hybrid models outperformed the corresponding transformer models by more than 2 points on average, similar to the original 4K evaluations. Moving on to tasks that necessitate natural language reasoning across long contexts, we evaluated the 16K and 32K model extensions on 9 common long context tasks. In this scenario, the base Mamba-2 hybrid and transformer models achieved similar accuracy on most tasks and surpassed the pure Mamba-2 model by more than 6 points. Both the 16K and 32K variants improved over the base models by an average of around 4 points, mainly due to a significant accuracy increase on tasks with lengthy inputs, such as narrative QA. When comparing the 16K and 32K Mamba-2 hybrid to the corresponding transformer models, we noticed that the transformer models performed better on certain tasks, particularly multi-document question-answering tasks like hotpot QA. This led to the 16K and 32K transformer models achieving approximately 1 point higher average accuracy than the Mamba-2 hybrid models. We speculated that the lower accuracy of the hybrid model on these tasks might be because the SSM layer states sometimes get confused by irrelevant documents until the end of the sequence. The multi-document question-answering tasks in table were sourced from the long bench evaluation suite, which generates long context inputs by concatenating relevant documents with random paragraphs from Wikipedia. This confusion could be attributed to our method of packing unrelated sequences together for 16K and 32K inputs during continued pre-training, potentially causing the SSM layers to mistakenly link separate documents. While this approach is commonly used for transformers, it may not be directly applicable to hybrid models. Based on our observations, we also noted that hybrid models might be more sensitive to prompt formatting than transformer models. For instance, minor prompt modifications had a greater impact on the accuracy of the Mamba-2 hybrid 4K model compared to the transformer. We believe that future research should delve into studying the prompt robustness of hybrid models further and comparing aligned and instruction-tuned hybrid models with their transformer counterparts. Additionally, we evaluated the 16K and 32K hybrid and transformer extensions on synthetic tasks in the Ruler benchmark suite, which include tasks like needle in a haystack, NIA, and require tracing and aggregating information across contexts. The Mamba-2 hybrid models exhibited significantly improved NIA abilities compared to the transformer models and the pure Mamba-2 model. For instance, the 16K hybrid model achieved an average accuracy 13 points higher than the 16K transformer on these tasks. The transformer models struggled particularly with the variable tracking (VT) task, where they tended to directly copy answers from in-context examples instead of predicting the actual question output. Interestingly, while the hybrid model generally performed better on most tasks, the transformer consistently achieved higher accuracy on keywords extraction (KWE). We also observed that the hybrid model outperformed the transformer on the hotpot QA task in the ruler evaluation, contrasting the results from the long bench evaluation. This discrepancy could be due to the different context creation methods used in the two benchmarks. Furthermore, we evaluated the long context hybrid and transformer models on the synthetic phonebook task, which tests the model's ability to learn and copy information from the context. The results showed that the hybrid models could perform the phonebook task perfectly beyond their trained context length, while the transformer models started making mistakes as the phonebook length approached their trained context lengths. Lastly, we demonstrated that the hybrid architecture can extend to context lengths well beyond 32K by training a 128K model through continued pre-training. This model showed promising results on the phonebook task, performing perfectly up to and beyond the sequence length it was trained on. Overall, our evaluation highlighted the comparable or superior long context capabilities of hybrid models compared to transformers in most tasks, emphasizing the need for further research in this area. Section Summary. In this section, we evaluate the long context ability of hybrid SSM transformer models by training 16K and 32K variants and comparing them to corresponding transformer models. We extend the base models to larger context lengths through continued pre-training and observe that the hybrid models generally match or exceed the transformer models in tasks like phonebook and needle in a haystack, but may fall short in tasks like multi-document question answering. Further research into these areas and long context versions of hybrid SSM transformer architectures is encouraged. Section: Related work. In this section, we will discuss recent advancements in hybrid models that combine Mamba, attention, and MLP layers to enhance accuracy and efficiency compared to pure Mamba and transformer models. Previous studies have introduced Mamba attention hybrids to address the limitations of Mamba in context learning tasks. These hybrid models have shown improvements in inference speed and GPU memory usage compared to other models like Llama and Mistral. Jamba and Zamba have trained Mamba attention hybrids at a larger scale, demonstrating enhanced model accuracy and efficiency. Jamba incorporates a mixture of experts, MO, to increase the total model capacity without increasing active parameters. On the other hand, Zamba introduces a shared attention module and utilizes an annealing phase during training with high-quality datasets to enhance the hybrid model's quality. Our focus is on combining Mamba, attention, and MLP layers in hybrid models for a direct comparison with transformer baselines at larger scales, exceeding 7 billion parameters and 1 trillion tokens. Other recent studies have explored hybrid models that combine linear RNNs or convolutions with attention mechanisms to improve performance in various tasks. It is worth noting that the success of hybrid models seems to depend more on the relative proportions of each hybrid component rather than a specific architectural design or pattern. This insight contrasts with previous approaches that included an MLP layer after each attention layer, resembling transformers.